All right, welcome to lesson 2.5 on piecewise functions. My name is Mr. Teal, and I'll be taking you through this lesson today. So let's go ahead and get into a little introduction of piecewise functions. So a piecewise function, I had to double check the spelling on that one. I am not an English teacher. That is such an easy word to misspell. A piecewise function has different rules for different parts of its domain. We will explore functions that pair every number in an interval with a single value called step functions. Now, one such step function is called the greatest integer function, and this is y equals that little funky bracket of x, and that is going to be called the greatest integer function. And what that represents is the greatest integer less than or equal to x. So whatever the number is inside of that little bracket there, we are looking at the greatest integer less than or equal to that value. The format for writing a piecewise function is shown below. So we have f of x is equal to several different formulas, and these different formulas are going to have different criteria for when the formulas are going to be represented on our graphs, okay? So you're going to notice a lot of inequalities today when we're looking at piecewise functions, and those inequalities are going to tell us what areas of our domain we are going to represent each formula. So let's go ahead and get straight into it. Can you draw a piecewise function? So let's go ahead and make up a piecewise function right here. I'm going to go ahead and say f of x is equal to, and I have my little curly bracket here, f of x is equal to 1/2 x plus 3 when x is less than or equal to 2. And then I have f of x is equal to x minus 4 squared minus 3 when x is greater than 2. So as you can see, I have two different formulas happening here, and I have two different inequalities happening here. Now, I'm going to call this one formula 1, and I'm going to call this one formula 2. Let's go ahead and label those just so we can keep them straight. So for formula 1, I'm only going to graph formula 1 when x is less than or equal to 2. So looking at all of the spots on this graph where x is less than or equal to 2, I'm going to have my 1/2 x plus 3 line. That's going to be graphed only when x is less than or equal to 2. Now for function number 2, I have x minus 4 squared minus 3. I'm only going to graph this function when x is greater than 2. So on the right-hand side of this graph, I'm going to have the graph of this function, okay? So these two inequalities right here tell you when you are starting your function and when you are stopping your function. So we are going to be starting formula number 1 on the left-hand side, but we are going to stop when x is equal to 2, because the left-hand side is the only place that I can graph this. This is my graphing criteria. On the alternative, I have x minus 4 squared minus 3. I'm only going to graph this when I start at 2 and go to the right. Okay, so I'm going to have essentially two different graphs happening on the same exact coordinate plane. Okay, so let's go ahead and see how this works. So if I am looking at 1/2 x plus 3, I have x is less than or equal to 2. Notice how I have an equal sign underneath this equality. This means I'm going to have a solid dot at 2. Okay, and then also notice for function number 2, I don't have an equal sign here. So this means for graph number 2, I'm going to have an open dot at 2. Okay, so let's go ahead and draw a couple of different tables. So I'm going to go ahead and put my tables over here just to keep them nice and organized. So for my first function, I'm going to be looking at 1/2 x plus 3. So again, I am only graphing 1/2 x plus 3 when x is less than or equal to 2. So the only numbers I'm going to put on my table are numbers that are less than or equal to 2. So let's go ahead and put -1 first. So if I plug -1 in for x, I'm going to have 1/2 x times -1. I don't like that actually. I'm going to put an even number. You guys, I don't want to mess with fractions. So always try to plug things in. They're going to be clean numbers. If you don't have a clean number that comes out, it's just going to be hard to graph. So I'm going to go ahead and change this to -2. I hope that's all right with everybody. So 1/2 times -2, that's going to be -1. -1 plus 3 is going to be +2. So at -2, I'm going to have +2 for y. So I have -2 comma +2. Okay, then let me plug in 0. So at 0, I have 1/2 times 0, that's 0. 0 plus 3 is 3. So on my y-axis here, I'm going to put 0, 3, okay? And then let's go ahead and plug in 2. Once again, we're going to have a solid dot at 2, so that's acceptable. So if I plug in 2, because 2 fits that criteria right there, 2 is less than or equal to 2, I'm going to say 1/2 times 2 plus 3. Well, 1/2 times 2 is 1. 1 plus 3 is 4. So at positive 2, I'm going to go up 4. Now, can I graph, say, positive 4 for an x value? Well, I can't because 4 is not less than or equal to 2. So once again, I can only use values that are less than or equal to 2, because once we get any farther to the right of 2, we are going to be moving into equation number 2, okay? So that means that right here, that is where we are going to stop. This is the big point of the graph here where we need to pay attention, okay? We are going to stop our graph right here. So I'm going to go ahead and graph this, but I'm going to be careful not to cross that line. So all to the left of that line right there is going to be the graph of 1/2 x plus 3. Okay, so now we have graphed the first side of that equation. Okay, now let's look at the second part of the piecewise function. So I have x minus 4 squared minus 3 when x is greater than 2. So let's go ahead and put another table down here. So I'm going to say this is x minus 4 squared minus 3. I have x and y here. Now I'm going to go ahead and start at 2, because keep in mind we're going to have an open dot at 2. So I'm still going to graph this function at 2, but just keep in mind we are going to have an open dot at 2. So let's plug in 2. So if I plug in 2 here, I have 2 minus 4 squared minus 3. Well, 2 minus 4 is negative 2. Negative 2 squared is going to be positive 4. Positive 4 minus 3 is going to give me 1. So at 2, 1, I'm going to go ahead and graph this. Once again, we are having a solid dot at that point. So 2, 1, I have an open dot here. So now I'm going to plug in some other values. Once again, we're only plugging in values that are greater than 2. So what's a value that's greater than 2? Well, let's go ahead and do, 4. So if I plug in 4 here, I have 4 minus 4 squared minus 3. 4 minus 4 is 0. 0 squared is 0. 0 minus 3 is negative 3. So at 4, negative 3, I'm going to plot a point. Once again, this is a parabola, okay? This follows the parabola form, so make sure we are not drawing this as a straight line, but rather a parabola. And let's go ahead and do another point. So if I plug in, say, positive 6, 6 minus 4 squared, well, 6 minus 4 is 2. 2 squared is 4. 4 minus 3 is going to give me 1. So at 6, I'm going to go up positive 1, okay? So I'm going to go ahead and make those into a parabola shape. Try to make this as smooth of a curve as possible. So now I have graphed the right-hand side of that function. So once again, this criteria here is very important. We know that something big is happening at that graph x is equal to 2. Okay, so that's kind of like my asymptote, sort of. That's where I'm stopping and starting the function. So the first function is on the left-hand side, but that function has to stop here. Since I have a solid line under here, I have the equal sign under the inequality. That means that I'm going to have a solid dot for the first function. And then for the second function, I don't have the same line. So that means I'm going to have an open dot. And the second function starts at x equals 2. As once again, the second function is represented by all values greater than 2. So that is how you graph a piecewise function. So let's go down to example number 1. We're going to graph the absolute value function using this piecewise. So what I'm going to do is I'm going to draw 2 different tables. I'm going to draw a table for function number 1. So let's go ahead and draw a table for number 1. And I'm going to label this. I want to be very, very clear about which line I'm talking about. And I'm also going to put one down for equation number 2. All right, so let's go ahead and take a look at our criteria. So for equation number 1, my criteria is x has to be greater than or equal to 0, okay? So that means that this is going to represent all of the values that are greater than or equal to 0. Notice how at 0, I'm going to have a solid dot because I have the equal sign. So I'm going to say solid dot at 0 for function number 1. Okay. So since we're talking about all values greater than or equal to 0, let's go ahead and start with 0. So I'm going to plug in 0 to function 1. If I plug in 0 to function 1, I just have x. So if x is equal to 0, That means y is also equal to 0. And once again, this is going to be a closed dot here. I'm going to say closed dot here. Okay, now let's go ahead and do all values that are greater than or equal to 0. So I'm going to look at 1 here. If I plug in 1 to that function number 1, I'm going to get out a positive 1. So 1, 1 is going to be my next point. Let's go ahead and do a couple more. So if I plug in 2, I'm going to have a positive 2. And if I plug in 3, I'm going to have a positive 3 come out. Okay, so I'm going to go ahead and graph this. Now let's be very careful. We're going to put a dotted line over here at x equals 0 just to kind of show us that that is where our graphs are going to start and stop. Okay, so if I'm looking at all values greater than or equal to 0, that means I'm looking at the right-hand side of this graph. All of these x values are greater than or equal to 0. If I'm looking at 0, 0, I have a closed dot here. So I'm going to go ahead and put a closed dot at 0, 0. Then at 1, I'm going to go up 1. At 2, I'm going to go up 2. And at 3, I'm going up 3. So I have now graphed the right-hand side of that piecewise function. Now, once again, we cannot draw this line all the way to the left-hand side because on the left-hand side, we have a different equation happening. So let's go ahead and look at equation number 2. So this says f of x is equal to negative x if x is less than 0. So we're only going to be looking at x values that are less than 0 here. So let's think of an x value that's less than 0. Well, I can put negative 1 down here. Also, a quick note, I am going to have an open dot at 0 because we're not including 0. So if I were to put 0 here, I would get out 0. But once again, that is going to be an open dot at this 0, 0. Okay? So now let's go ahead and do all values that are less than 0. So let's plug in negative 1. If I plug in a negative 1, I'm going to have a negative, negative 1. Negative times negative is a positive, so that's going to come out positive 1. If I plug in a negative 2, I'm going to get negative, negative 2, which comes out positive 2. And same thing if I plug in negative 3. Negative, negative 3 is going to come out positive 3. So let's go ahead and graph those. So at this one, I'm going to have an open dot. But keep in mind that the other function already takes care of that point, so we're good to go. Negative 1 up 1, that's going to be right here on the graph. Negative 2 up 2 is right here. Negative 3 up 3 is right here. So I have now graphed the left-hand side of that piecewise function. So this is going to be the graph of my piecewise function. I have equation number 1 on the right-hand side and equation number 2 on the left-hand side, and we paid very close attention to the criteria. Let's go down to example number 2. So we're going to graph f of x is equal to negative 2x plus 3 if x is less than 2. Now we're also going to graph x minus 1 if x is greater than or equal to 2. So let's go ahead and put a couple of tables down. First, I'm going to label those 1 and 2, and then I'm going to be very careful to stay consistent with my tables. So for equation number 1, here's going to be my table, xy. For equation number 2, here's going to be my table, xy. Okay, so let's look at equation number 1. So this says all values if x is less than 2. We're also going to include 2 here, but we're going to keep in mind that since there is no equal sign under that inequality, there's going to be an open dot here. So if we were to plug in 2 to this equation, negative 2 times 2 is negative 4. Negative 4 plus 3 is going to give me negative 1. So I'm going to have negative or positive 2, negative 1. I'm going to be very careful here. Let's go ahead and highlight this. Once again, there is going to be an open dot here at 2, negative 1 because it is not included in the graph. All right, now we're going to look at all values less than 2. So now let's think of another x value that's less than 2. I can plug in a 1. So negative 2 times 1 is going to give me negative 2. Negative 2 plus 3 is going to give me positive 1. So I have a point at 1, 1. Another value that's less than 2, let's do 0. 0 is nice and easy. So if I have negative 2 times 0, that's just 0. 0 plus 3 is 3. Let's do one more. So one more value that's less than 2 is going to be negative 1. Negative 2 times negative 1 is positive 2. And then positive 2 plus 3 is going to give me positive 5. All right, so let's go ahead and graph this. Remember, we're just graphing this at x is less than 2. So at x equals 2, I'm just going to put a dotted line because this is going to tell me where I'm starting and stopping that function. Once again, we get this dotted line from these inequalities right here. This tells you there's a dotted line at x equals 2. Okay, so if I'm talking about all the values that are less than 2, I'm talking about all of the values that are to the left of that line. So let's go ahead and do those here. At 2, -1, I'm going to have an open dot. Okay, let's make sure we highlight that so we can see we have an open dot here. Okay, then at 1, 1, I'm going to have a point right here. At 0, 3, that is going to be my y-intercept right here. At -1, 5, that is going to be right about here. So that is the graph of the left-hand side of that piecewise function. All right, so we have successfully graphed the left-hand side. Now let's look at the right-hand side. So at x minus 1, this is graph number 2, we have x is greater than or equal to 2. So let's go ahead and include 2 here. If I plug 2 into that function, 2 minus 1 is 1. So that means at 2, 1, I'm going to have a solid dot. I'm just going to go ahead and highlight this, make sure we know that this one is the solid dot, or the closed dot. Okay, so let's go ahead and look at some more values. So greater than or equal to 2, I can do 3. 3 is greater than or equal to 2. If I plug in 3 here, 3 minus 1 is going to give me positive 2. Another value that's greater than or equal to 2, that's going to be 4. So if I plug in 4, 4 minus 1 is going to give me 3. Okay, now let's plug in one more. If I plug in 5 to equation number 2, 5 minus 1 is going to give me 4. So I have 5, 4. All right, let's go ahead and graph those values. So at 3, 2, I'm going to plot a point. At 4, 3, I'm going to plot a point. And at 5, 4, I'm going to plot a point. Also, I forgot to plot my 2, 1 point. So at 2, 1, I have a solid dot here. So this is going to be the right-hand side of my piecewise function. So be very careful to make sure you know which equations you're talking about, what the criteria are for those equations, and that is how you're going to graph a piecewise. Moving on to example number 3. So this is not about graphing. This is more about figuring out if I have a value and I have a piecewise function, what is the evaluation of that x going to be? We have to be very careful to pay attention to the criteria here. So if we have f of x is equal to -x minus 3 when x is less than -2, we have f of x is equal to 1 when we have an x value between -2 and +2, and we have 1/2 x plus 2 when x is greater than or equal to 2. So if I am trying to evaluate f of 8, I have to figure out where does this fit in. Okay, so which club is this one going to be a part of? Well, in order to be the -x minus 3 club, this value has to be less than -2. Is 8 less than -2? No, so that means it is not going to be equation number 1. Now let's look at this one. If f of x is equal to 1, that means that, our value has to fit into this club. It has to be between -2 and +2. Is positive 8 between -2 and +2? No, so it's not part of this club. But let's see if this value fits into the third club. So 1/2 x plus 2, this means that x has to be greater than or equal to 2 in order to join the club. Well, hey, 8 is greater than or equal to 2. So that means we are going to be looking at the third club. Okay, f of 8 fits into the third club because 8 is greater than or equal to 2, and that works out. Okay, so what this means is once we figure out which club that value fits into, we're going to plug in the x value to that club. So we're going to say, I'm going to write this in a different color. So we're going to go ahead and write 1/2. We're going to plug in 8. So 1/2 of 8. And, I'm losing track of my things here. 1/2 of 8 plus 2. Well, if I have 1/2 of 8, that is going to be 4, and then 4 plus 2 is going to give me 6. So f of 8 is equal to 6. So always figure out which club it fits into first, and then whichever club it fits into, plug the value into that club's equation. Let's look at f of 0. So first of all, which club does f of 0 fit into? Well, it doesn't fit into club number 1 because 0 is not less than -2. Does it fit into club number 2? Is 0 in between -2 and +2? Yes, so I'm going to say this is in the second club. So that means we're going to plug this into the second equation because -2 is less than or equal to 0, which is less than 2. Okay, so it fits into the second club. So f of 0, as we can see, f of x is equal to 1 for all values of x in between here. So what that means is f of 0 is simply going to be equal to 1. Okay? Looking at part C, f of -5. Let's figure out which club this fits into. So if we're looking at -5, does it fit into club number 1? Is -5 less than -2? Well, yes, it is. So I'm going to say this is in the first club because -5 is less than -2. All right, so it works out. So we're going to plug this into the first club. So let's go ahead and plug this in. The first club's equation is -x. So instead of -x, I'm going to write -5 minus 3. Well, if I have -5, that's going to be +5. +5 minus 3 is going to give me +2. All right, so the answer here is +2. All right, let's look at example number 4. So I have f of x is equal to -2 times the absolute value of x minus 1 if x is greater than or equal to -1. I have f of x is equal to 3 if x is between -4 and -1. And I have -1/2 x minus 1 if x is less than or equal to -4. Our first one, A, is f of 6. So let's figure out which club this one is part of. So if I'm looking at the first club, x has to be greater than or equal to -1. Well, is 6 greater than or equal to -1? It is, so this is going to be part of the first club. And that is because 6 is greater than or equal to -1. It works out. So let's go ahead and plug this into the first equation. So I'm going to say -2 times the absolute value of x minus 1. Instead of x, I'm going to go ahead and write 6 minus 1. And so the absolute value of 6 minus 1, well, 6 minus 1, that's going to give me 5. The absolute value of 5 is just 5. So I have -2 times 5, which is equal to -10. So my answer here is -10. All right, moving down to part B. If I have f of -2, let's figure out which club this is part of. -2, is -2 greater than or equal to -1? It is not. -2 is less than -1. Is -2 in between -4 and -1? It is. So that means I'm going to be part of the second club, right? And that is because -4 is less than -2, which is less than -1, and that works out. So for the second club, all of our y values are going to be 3. So that means if we plug in -2, we're just going to get out 3. So I'm going to say f of -2 is just equal to 3. Simple as that. Last but not least, I have f of -8. Let's figure out what club that one is a part of. So if I look at the first one, -8 is not greater than or equal to -1. -8 is not in between 4 and -1, so it's not part of club 2. But -8 is less than or equal to -4. So that means this is going to be part of the third club. Okay, and that is because -8 is less than or equal to -4. It works out. So let's go ahead and plug -8 into the third equation. So I have -1/2 times, I'm going to plug in -8, and I'm subtracting 1. -1/2 times -8, well, a negative times a negative is a positive. 1/2 times 8 is 4, so that's going to be equal to 4 minus 1, which is 3. And that is how we evaluate a piecewise function. Let's go ahead and move down to example number 5. This is graphing step functions. So we're going to evaluate the greatest integer function, and that means that we are answering the question, what is the integer not greater than some value? Okay, this is actually a little bit tricky to get at first, but it is super easy once you get the hang of it. So what we're looking at, if we look at part A, we're trying to find the greatest integer of 2.3. So what is the integer not greater than 2.3? So essentially we are rounding down because we want the nearest integer that is not greater than that number. So if we were to round this down, we would get 2, all right? 2.3 rounds down to 2. 2 is the integer that is not greater than 2.3. So the answer is just 2. So in other words, I want you to always round down when you are looking at step functions. Okay, let's look at part B. What is the greatest integer of 3.4? Again, we are always rounding down because we're trying to find what integer is not greater than 3.4. Well, that integer is just going to be 3. Let's look at part C, 0.57. What is the integer not greater than this? We can't go greater than this. Well, the nearest integer that's not greater than that is just going to be 0. We always round down. Part D, what is the greatest integer of 7.9? Well, we're looking for a number that's less than 7.9. That's a whole number. The number that is less than 7.9 that's whole is 7. Be very, very extremely careful with part E, part F, part I, and part G. Why do you need to be careful with those? Because there are negatives. I want you to think about the number line when you are doing these greater integer functions. If we are looking at the number line, we have 0 in the middle, positive numbers on the right, negative numbers on the left. We know that all of the numbers to the left are going to be the smaller numbers. So if we're comparing two numbers, the number that's more to the left is going to be the smaller number. The number that is more to the right is going to be the more positive number. So if we are looking at the integer that is not greater than negative 4.6, which means it has to be to the left-hand side on the number line, that means we are going to have to round this down to negative 5. Now you're like, what? I thought that we had to round it to negative 4. Well, keep in mind, negative 4 is technically a larger number than negative 4.6 because it falls farther to the right. So if we look right here, let's say this is negative 4.6. Let's say this is negative 4. All right. We know that the more to the left we go, the smaller we get. So that means negative 4 would be on the right-hand side. We are looking for the number that's smaller, which is on the left-hand side. So that means this would be negative 5. Same thing if we're looking at F. What is the greatest integer of negative 0.85? Once again, we're looking for the smaller integer. So we're rounding down. We're going to the left-hand side on the number line. So that means we are actually looking at negative 1. Okay. With part G, negative 2.4, we're looking for the greatest integer. So what is to the left-hand side on the number line? Which number is smaller, whole number? We are looking at negative 3, because negative 3 falls to the left-hand side on the number line. Now, part H, we're going back to positive numbers. Thank goodness. Whew, take a breath. What is the greatest integer of 9.7? Once again, if we're looking at the greatest integer, what is the integer that is not greater than 9.7? That means we're rounding down to 9 because 9 is more to the left on the number line than 9.7. Part I, we're going back to negatives. Negative 1.1. Now, if we're looking at negative 1.1, I want the integer that's more to the left on the number line. So that is going to be negative 2. So if you need to, always visualize that number line, which number or which integer falls to the left-hand side of that decimal on the number line. So I'm going to write left-hand integer on number line. Okay. Let's go ahead and move to the very last page. So example number 6, I want you to figure out how we're going to graph these step functions. So each piece of the graph is going to be a horizontal segment that is missing its right endpoint. The open circle indicates that the right endpoint is not part of the graph. Let's go ahead and figure this out by first drawing a couple of tables. So if I have x, y, and we're looking at the function f of x is equal to the greatest integer of x. Okay, I'm going to go ahead and plug in a couple of values. So let's go ahead and first plug in 0. So if I am plugging in 0, what is the nearest integer to 0? Well, 0 in and of itself is an integer. So I'm going to say that is equal to 0. Let's go ahead and plug in something like 0.5. Okay, so what is the greatest integer to 0.5? So again, that is the integer that is more to the left on the number line than 0.5. That is going to be 0. Let's talk about 0.9. So what is the integer that's more to the left on the number line than 0.9? That is still going to be 0, because once again, we're rounding down. If we're looking at those decimals, we're going to the left on the number line. But then if we actually put in 1, keep in mind that 1 in and of itself is an integer. So that means if we plug 1 into this function, we're just going to get out 1 because this function always outputs integers. So if we plug in an integer, we're going to get out that same integer. So if we were to graph this on our graph right here, 0, 0, that would be a solid dot. So I'm going to put a solid dot here at 0. Then at 0.5, that's somewhere right here in between 0 and 1, that's still going to be 0. 0.9, that's still going to be 0. But then at 1, we jump up to 1. That's why it's called a step function, because it steps up. Now, always note that what we're going to do here, because all of these values until we get to 1 exactly, so even 0.9999999, that's still going to be at 0. So at 1, we're just going to put an open dot, because that allows us to draw this line right here. And something I want you to notice is this is going to be a common trend for each of our steps on this graph. So if we're looking here, if we're at 1, 1, and then we look at 1.5, well, 1.5 is still going to round down to 1, so our output is still going to be 1. 1.9999999 is still going to be here at 1 until we get to 2, because then if we plug in a 2, we get out a 2. So what this means is we're essentially creating a set of stairs, right? And this is going to be the same for every single point on that graph. That is what our graph is going to look like. So it's called a step function because it looks like stairs in Mr. Teal's house. Okay, let's go ahead and go to example number 7. So we are going to write the piecewise that represents the graph. So what we did last time is we talked about, okay, well, if I have an equation, how do I actually graph it? This time we're going to go in reverse. So what I want you to do first is I want you to figure out where your open dot and your solid dots are, because that line right there is going to tell you where your inequalities are going to lie. Okay? So let's look at the left-hand side first. So on the left-hand side, this is all values where x is less than. Since this is a solid dot, it's going to be less than or equal to. So we are looking on the left-hand side at x is less than or equal to -2. So let's go ahead and figure out what this equation is. So this is obviously a linear equation. So I can go ahead and figure out what the slope is, and then I can use that to try to actually figure out what the equation is. So if I'm looking at my slope here, I have a point right here and a point right here. So that means my slope is going to be up to the right 1. So I'm going to say up to the right 1 is my slope. Okay, so I'm going to have some sort of an equation that has a positive slope of 2. So I'm going to have 2x. And then let me figure out what my y-intercept is going to be. So if I were to keep going, I'm going to use a pencil for this. If I were to keep going, let's figure out what that y-intercept would be. So if I go up to the right 1, up to the right 1, that would mean that my y-intercept of this line would be 5. But again, we stop here, so we don't see what the y-intercept is. But just with the pencil, I want you to note that if this line were to keep going, our y-intercept would be 5. So the equation of this line is going to be 2x plus 5. Okay? And then we can go ahead and erase that because that's actually not part of our graph. Okay, now looking at the second part of it. So the right-hand side, we have our line starting here, open dot, and we're going to the right-hand side of -2. So this is going to be all values of x that are greater than -2. We're not including -2 because we have an open dot here. Okay, so first of all, let's figure out what our slope is. So our slope, if we're starting here, is going to be up 1. Let's see, we have a point right here at 0,4. So that's going to be up 1 to the right 2, up 1 to the right 2. So my slope of this line is going to be up 1 to the right 2. So I have 1/2. So that means this graph is going to be 1/2 x. And then I already have my y-intercept. My y-intercept is 4. So that is plus 4. So that is how we're going to go in reverse and actually write out the equations of a piecewise graph. All right, last example, example number 8, we're going to write the piecewise function that represents the graph. Oh my goodness, we have so much going on here. So I'm going to put a dotted line through wherever I have a solid dot and an open dot. So let's put a dotted line right here because I know I'm going to have some inequalities here. Let me put a dotted line here. So this looks a little different than the last one because this has 2 dotted lines instead of just 1. So this means we're going to have 3 different components of our piecewise function. So let's go ahead and figure out what that means. So let's look at the left-hand side first. So the left-hand side of this graph is going to be for all values that are less than 2. And then once again, that is going to be an open dot here. So that means that we are going to have just a less than sign. So for the first part of this, I'm going to say x is less than 2. Now let's figure out what equation represents that graph. Now obviously this graph is a parabola. My vertex is down here at 0, -3. So if you remember how we actually graph or write the equation of these parabolas, you might remember that we have y equals x squared. That is the parent graph. So that's when our vertex is at 0, 0. But since our vertex here is at 0, -3, we essentially have shifted the graph down 3 points. So that means this is going to be x squared minus 3. So at x is less than 2, our graph is x squared minus 3. Okay? Now let's go ahead and look at the middle section. So in the middle section, we have x is equal to 2 here on the left-hand side, and we're going all the way until x is not equal to 5, but we are at 5 with an open dot. So what this means is at 2, that's our starting point, and we are including it. So we're going to have 2 is less than or equal to all values of x in between 2 and 5 are going to be right here on this graph. So I'm going to say x. And since we have an open dot here, I'm not going to include it. I'm going to say less than 5. So we have 2 is less than or equal to x, which is less than 5. That is what we're looking at here in the middle. Now let's figure out what that line is. Since I have a horizontal line, that means I'm going to have y equals something. My y value is 3, so this is going to be y equals 3. Now, since we're looking at a piecewise, you don't actually have to write the y equals. We're just going to have 3 right here. Okay, let's look at the last part here. So if I'm looking at the right-hand side, I'm starting at 5 and I'm going on forever. So this means all values of x that are greater than or equal to, I have a solid dot, so I put equal to 5. And let's figure out what that graph is going to be. So if I'm looking at this right here, I can see that my slope is going to be down 1 to the right 1, down 1 to the right 1. So my slope here is going to be -1, okay? And if you want to go in reverse and find out what your y-intercept is going to be, we're going to go up 1 to the left 1, 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 up 1 to the left 1. This means that our y-intercept would be right here at 0, 7. So I'm going to say this is equal to -x plus 7, okay? So that is how you graph piecewise functions. That is how you evaluate piecewise functions, graph step functions, evaluate step functions, and finally, figure out how to write the equation of a piecewise function. Thank you guys for tuning in. Please make sure you do your homework assignment that's associated with this lesson, and we will see you back here next time.